Hello student, welcome to the Power Electronics lab. In this section we are going to learn experiment Introduction to Power Electronics lab, simulation and hardware setup on half-wave diode rectifier. From this experiment, learning outcomes, understanding the simulation of power electronics circuit in Simulink, understanding the power GI block for FFT analysis of the circuit simulated, understanding the hardware implementation of power electronics circuit. Familiarization with MATLAB Simulink. Start on MATLAB once MATLAB is launched. Open New or Simulink. Now this has a MATLAB icon window. Double click on block model and save the new .slx file. Double click on the block model. Now you will get as a untitled window. This untitled window save with some file name. Now click on Simulink library. This is a Simulink library. To open the Simulink library browser. Now in power electronics, this is a path. First select as a Simscape. Under Simscape, electrical. Under electrical, specialized power system. Under this, fundamental block. If you select fundamental block, these are the fundamental block. In this, power GI, power electronics blocks, measurement block, elements block, electrical source blanks. Now select as a power electronics or double click power electronics. Now you will get as a all power electronics blocks. Select as a electrical sources. So you will get all electrical sources. Select, double click on measurements. Now you will get as a measurement blocks. Now you need a mean RMS block. For this, select control and measurement. In that, select, double click on measurement. Now you will get a mean and RMS block. Now double click on element. You will get on all the blocks. In that you have to choose series RLC branch. Double click on sync. You will get on all the sync blocks. In that, scope and display you will select. Double click on source. You will get all the sources. In that, pulse generator, sine wave will be used. If you know the exactly name of the block name, so here you can type it and search it. You will get directly that block. MATLAB simulation implementation on half-wave diode rectifier with R and RL load. Now input voltage 50 peak equal 35.35 RMS and frequency 50 Hz. In first circuit, as a R, the resistance value is 100 ohms. In second circuit, RL, R is 100, L is equal 20 milli to 100 milli. MATLAB 19A simulation block and path. Suppose you need all these blocks, use this path. Now you want to do as a FFT analysis. In the configuration properties, go to logging, check log data to workspace, save format, structure with time, apply and OK. Now we'll do the simulation. For this, on the desktop MATLAB icon window, double click this MATLAB icon. Double click on Simulink In the Simulink, double click on block model. So your model is open with Untitled. This one you have to save with some file name. For this, go to File, Save As. Now I am giving some x-axis. Save it. Now your model is saved with XXX. You can give any file name. Now here you are designing your simulation circuit. For this you need any blocks. Go to library browser. In that our path is power electronics path is first select Simscape. Under this electrical specialized power system fundamental blocks power GI select add to your model power electronics select diode add to model go back double click measurement select voltage measurement add to model select current measurement add to model go back double click measurement in that select as a series RLC branch add to model go back double click electrical source in that select AC voltage source add to model. Now you need a bus selector for this Simulink commonly used block. Select bus selector add to model. Now you need a scope and display for this Simulink sync. Double click sync. Select scope add to model. Select display add to model. Next you need a mean and RMS block, control and measurements. In that measurement, mean block, select add to model. Select RMS block, add to model. Okay, nice. Now you can separate all the blocks. Copy of one more voltage measurement. Select copy of one more current measurement. Now double click AC voltage source. Peak amplitude give as a 35.35 RMS and frequency 50. Now connect AC voltage source one terminal to current measurement plus terminal, current measurement negative terminal to diode anode terminal. Now in series RLC branch type select as a or resistance value is 100 ohms. Rotate this one, control plus R. From cathode to current measurement, negative terminal to load one terminal, load other terminal to AC voltage source other terminal. So instead of taking two currents, so select as a one current measurement. So this voltmeter will measure as a input voltage. Now double click bus selector, remove unknown signal. Now from diode M terminal to bus selector input side, remove unknown signal, select signals, diode voltage, select, diode current, select, apply and OK. So for this you can take one more scope. So here you are getting two signals, but scope and one terminal. Now we want to add one more terminal in the scope. So double click the scope, go to configuration properties, number of input port to 2, layout 2, apply and OK. Now this one connect to scope one terminal, that is diode voltage, second one to second terminal, that is diode current. Now here also you can increase the number of input point terminals to scope. Double click, go to configuration properties, number of input port to 3, layout is 3. Now first one as a input voltage, now this voltmeter will measure across the load voltage. Output voltage. Next, circuit current. Now select one more mean, select one more RMS. Now copy, display. Now this main block to current terminal, RMS to current, mean to display, RMS to display. This mean to output voltage, RMS to output voltage terminal, mean to display, RMS to display. Now we have to save your model by pressing save button. Now here your simulation time is 10 seconds, so you have to give 0.5 seconds. Run your simulation by pressing run button. Now in the main block, the fundamental frequency is 60, so change to 50. RMS block also fundamental frequency 60, change it to 50. Fundamental frequency 50. apply and OK. Now save your model. Again run your simulation. Now you got a mean current, RMS current, mean voltage, RMS voltage at fundamental frequency. Now you can see the input and output voltages and currents by double clicking the scope. Now the first waveform has a input voltage. Right click on the wave, configuration properties, in the signal label, input voltage. Apply and OK. Second one is output voltage. Apply and OK. This is output current. Output current. Apply and OK. Now you can easily identify which waveform is which one. So first is as a input voltage, second is output voltage, third is a output current. Now this waveforms you have to take a screenshot and save in the one folder. Now we have to do FFT analysis on the output voltage. For this, go to configuration properties, select logging, check log data to workspace, save format, structure with time, apply and OK. Close this. Now again we change the scope parameters, save your model, again run your simulation. Now here go to model configuration parameters, data import and export, select, uncheck single simulation output, apply and OK. Now we want to see the FFT analysis. For this, go double click Power GI, select tools, FFT analysis. Now input 1 as a input voltage, select as a input 2, that is output voltage across the load. Now fundamental frequency should be 50. Display style, select as a list related to fundamental and display. Now here 50 Hz as a fundamental frequency. Now we got an 100%. At this fundamental DC component 10.77, fundamental 17.09 peak, in that 12.09 RMS. THD, total harmonic distortion 45.30%. Now we want to calculate second harmonic, select as a 100 Hz, that is second harmonic. Now percentage is 14.14%. When it is 100%, you got these values. Now at 44%, what is this values you have to calculate. Now calculate as a third harmonic at 150 Hz. Now the percentage is 1.34%. Now you can calculate at 1.34 percentages. Now this one also you can take a screenshot and save in the folder. Now we'll do as a FFT on the output current. At fundamental DC component 0.1077, fundamental 0.1709 peak, in that 0.1209 RMS. Total harmonic distortion 45.30 when it is in fundamental frequency. This one also you can take screenshot, save in the folder. Suppose instead of display style you want to select as a bar, so bar relative to DC component and display it. Now this has a bar chart for output current. Now you can do as a output voltage as a bar chart. Select bar chart, bar relative to DC component, display it. Here we will, instead of in the list we are getting as a values, here we are getting as a bar chart. So first can choose list is better. Bar chart also you can attach in the, this one also you can take a screenshot. Now R load is over. Next we will do as a RL load. In R circuit, now we can diode to observe diode voltage and diode current. Double click this one. This has a diode voltage, this one is a diode current. When diode is on, the current is flowing, and during negative half cycle its diode is not conducting, that current is 0. This also take a screenshot, save in the folder. Now we'll do as a RL circuit. So double click this RLC branch type, select as a RL load. Now select inductance L value is 20 millihenries, apply and OK. Don't change this any other part, only instead of R we are connecting as a RL in series only. Now save your file or save your model. Again run your simulation by pressing run button. Now you can open the scope. Now you can see this is a, here some peak is coming, that is a effect of inductance in the output voltage. Now this output voltage you have to do FFT analysis. This one also you can take a screenshot. For FFT analysis, double click Power GI, go to Tools, FFT analysis. In that select as a second input 2. Select as a display style is list relative to fundamental. Now at 50 Hz fundamental frequency, now DC component is 10.83, fundamental 17.15 peak, in that 12.13 RMS. Total harmonic distortion 44.97%. Now we want to calculate as a second harmonic at 100 Hz. Now 43.74%. We want to calculate these values. Next, third harmonic at 150 Hz. The percentage is 0.86. When it is in 100%, you got these values. Now at 0.85%, you have to calculate these values. This one also you can take a screenshot, save in the folder. Now same circuit we have to do implement on the hardware. Hardware implementation on off-wave diode rectifier with R load. For this you require as a power module. In that power module will give as a 3-phase supply, single phase supply and DC supply. In that you have to choose as a single phase supply. And second one is SCR diode power module. In that we have to choose as a diode. And third one is the resistor load. Between red and block and red the resistance value is 100. So the resistance value R equal to 100 ohms. Now we want to see the waveforms, output voltage using digital storage oscilloscope. Hardware implementation on off-wave diode rectifier with RL load. So instead of R, now we are connecting R and L in series. Now we are measuring across R starting point and L ending point. Now between red and block we are getting as a output voltage across the R and L. Now we'll do the hardware on off-wave diode rectifier with R load. For this we required as a power module and SCR diode power module, resistive load and inductive load. Between black and red the inductance value is 6 millihenries. Between black and red resistive load is 100 ohms. Now in the power module we'll get as a 3-phase supply, single phase supply and DC supply. With the help of the power module we'll take as a single phase supply. Now switch on your 3-phase main supply, switch on your meter switch, switch on your MCB of power module, switch on the AC voltage source. Now we will make connection from the AC voltage to SCR diode power module input of the MCB. From phase to phase of input MCB, neutral to neutral of input MCB. From the output of MCB phase terminal to diode anode terminal, diode cathode terminal to load of one terminal and load other terminal to output of MCB neutral terminal. Now we'll make switch on the AC voltage source. Now switch on SCR diode power module MCB. Now slowly increase the voltage by pressing plus button, reaches to 35.35 volts. That is 35.35 as a RMS voltage. Okay, 35.4. Now we will consider as a 35.35. Now adjust this knob. You will get as a clear waveform. Voltage division button. Now you got an output across the R load. Now the waveform is moving. For this you can stop, set to 50%. Press this button. Now we got an output. From this you want to measure RMS, mean and frequency, peak to peak, maximum value by pressing measurement button. Now you got a mean and RMS value. These waveform you have to capture in the PC with the help of open choice desktop. Double click this open choice desktop. Select instrument. Select USB type. OK. Now you got our CRO TDS 2002B, and this waveform you have to capture. Press get screen button. And this waveform you have to save by using save as this waveform in the folder. Now we'll do the FFT analysis of the output voltage. For this, press mass function and cursor on. Now use this knob, adjust the first fundamental frequency as a 50 Hz. At 50 Hz, we got a dB value 25.1 dB. So using this value, you have to calculate as a V fundamental RMS. That formula is 20 log V RMS equal to dB value. Now we want to calculate as a V RMS equal to inverse of 20 log and your dB value. Then you will get as a V RMS at fundamental. This fundamental dB value you have to capture in the PC with the help of the open choice desktop. Open choice desktop and select instrument USB. OK. Now press get screen. Now you got an FFT at fundamental frequency 50 Hz. Now your dB value is 25.1 dB. For this we'll do as a second harmonic at 100 Hz and third harmonic is 150 Hz. Now you can capture any one of the fundamental frequency. Now we'll do as a second harmonics. Now frequency at 100 Hz. Adjust this cursor to knob to 100 Hz. At 100 Hz, your dB value is 17.5 dB. This also you can calculate as a V fundamental RMS with the help of that formula. Now we'll do as a third harmonic at 150 Hz. Adjust this knob to 150 Hz. Now you got the cursor at 150 Hz. Now you got a dB value is minus 19.7 dB value. Now this value also you can convert into V fundamental RMS. Now we'll do as a RL circuit for this. Now make it SCR diode power module MCB should be off and remove one of the load terminal, resistive terminal, and from the resistive other terminal to inductor one terminal as a block terminal. From the inductor other terminal, that is red terminal, to MCB neutral terminal. Now circuit is connected as a R and L. Now we will measure across the R and L, R starting point and L ending point. Now connect this probe also. One is the R starting point, that is as a positive, L ending point as a negative. Now we can observe the positive terminal at R starting point, negative is L second terminal. Switch on SCR diode power module and adjust the input voltage to 35.3 and you got an output voltage across R and L. Now you need an RMS and mean values. For this, press the measurement button and from this you can observe the RMS value and mean value, frequency, peak to peak and maximum value. Now these waveform you have to capture in the PC with the help of open choice desktop. Select instrument, select USB, OK, and get screen. Now these waveform at R and L. This waveform you have to save as in the folder. For this output voltage we'll do as a FFT analysis. Press mass function and press cursor button. Now adjust this knob to fundamental frequency as a 50 Hz. Now your cursor placed as a 50 Hz. Now you got a dB value 25.1 dB. This value you have to calculate in the V fundamental RMS and a formula 20 log V fundamental RMS equal to dB. Now V RMS fundamental equal to inverse of 20 log dB value. Then you will get as a V fundamental RMS at 50 Hz. This FFT analysis you want to capture in the PC. Open the Open Choice desktop. Select instrument. Select USB. OK. And press Get Screen button. Now this one you have to save as in the folder when frequency at fundamental frequency. Now we'll do as a second harmonics. For this, change the knob to second harmonic at 100 Hz. Now we got a 71 dB. This value note down in the observation. Now we'll do as a third harmonic. Adjust the cursor knob to 150 Hz. At 150 Hz, so the dB value is 19.3 dB value, and calculate of second harmonic and third harmonic. In these values you have to find in the V fundamental RMS. Now we'll done on the FFT analysis of RL load, and previously we have done as a RL load FFT analysis with the help of this. So you have to calculate your V fundamental values for different harmonics and output voltage. All this resultant you have to put in the tabular column and result file. Now we are done the hardware part on off-wave diode rectifier with R and RL load. We captured all the voltages and waveforms FFT analysis for different frequencies. So we have done R load and RL load on the off-wave diode rectifier. From this we got all these values. With this we are completed on off-wave diode rectifier with R and RL load. Observation and results for R and RL load. In the simulation we have already saved all the screenshot files. Here you have to attach your screenshots. Attach the waveform of input, output current and diode voltage and diode currents. Now second one, attach the waveform of FFT plot of output voltage, FFT plot of output current in Simulink. Third is attach the waveform of output voltage FFT plot from the experimentally. Calculate performance parameter, theoretically, simulation values and hardware values. FFT calculation from the simulation from hardware part. Here it is given total harmonic distortion formula, VAC RMS formula. Now V fundamental RMS from the experimental you are getting as at different harmonics you are getting as a dB value. Now this one you have to convert into V fundamental RMS equal inverse of 20 log dB value. Then you will get as a V fundamental at different harmonics. Thank you.